Suppose that I have a bit of string hanging from a support or the ceiling, and I attach my little yellow ball to the other end of the string. So I have a pendulum. Okay. I can just let go of the ball and it will just swing back and forth like a pendulum always does. But this time I'm not going to do the normal pendulum. Instead of just letting it go like that, I'm going to give it a push in the perpendicular direction. So what happens is that instead of just falling towards this vertical axis, the ball is going to go around the axis in a circle. Now, of course, I have to push it with just the right velocity. Okay, otherwise it will go around in some other shape. Okay, I need to give it a push in with exactly the right velocity in a direction that is perpendicular to this plane, this vertical plane containing the line and the vertical. So I need to push it with some velocity, and then if I get the velocity exactly right, I might have to try it a few times. I might have to push. If I push it too gently, it would just do the original thing, maybe with a little wiggling here and there. If I push it too hard, it will go too far to that way, and it will maybe make a big oval-shaped motion. So assuming that I get it just right, after some trial and error, it will go around in more or less a circle. And what it seems like it is doing is that this string would trace out, actually it would look like it traces out the surface of a cone. And for this reason, this pendulum has a name. It is called a conical pendulum. So this word conical pendulum describes a pendulum that moves in this way. Now what I want to do now is this. I want to find this velocity. So let's see how to do that. Now I need some information. Suppose that okay, I would need this angle. So suppose that this angle is 30 degrees. I would need the mass of the pendulum. Let's say this, or the little ball. Let's say this is 0.01 of a kilogram. Let's see, what else do I need? I need the acceleration due to gravity, g. So g is 9.81 meters per second squared. That should be all I need. Yes. So now I have this problem. Given this that I want the little ball to go round as a conical pendulum with an angle of 30 degrees to the vertical, given that it has mass of 0.01 kilogram, what velocity must I throw the ball at in this direction, that is at 90 degrees to this vertical plane? In order to do this problem, I need to think about the forces on this pendulum. Now, if we think about the forces, there is the weights, obviously, the weight that pulls downwards. So that's the weight. I'll call that mg, mass times acceleration due to gravity, and that's the mass, the 0.01 kilogram. Now, there is another force, and that's the tension in the string that pulls at it. So that's the other obvious force. The string that we can see, I'll call that T. And there is no other force. There is no other force. Now, at this point, it is very important to clear up one confusion, if I may call it one important confusion that happens often when doing such a question, especially after we have learned about centripetal force. Now, before we have learned about centripetal force, or maybe even after, it is common to think that there must be a centrifugal force pulling this outward. Okay, but I've already explained previously that that's not real. Now, but after we have learned about centripetal force, we all understand that there must be a force pulling it towards the center. So it is therefore natural to think that apart from the obvious weight and force tension along the string, obviously there must be a centripetal force as well. So therefore, we have altogether 1, 2, 3 forces. Now, unfortunately, that's wrong. That's wrong. For a very simple reason. Okay, at least the first reason is very simple. The simple reason is that if you just look at this, picture, as we have seen, there's obviously the weight on the ball. There is the tension from the string, and that's all. We don't see anything else that can give any other force. So it is not possible that apart from those two forces, there is an additional centripetal force. Now, then you may ask, if there isn't this centripetal force acting on it, if there isn't this third force acting on it, then how can it go around in a circle? Right? I've already said many times that in order for the ball to go around in a circle, we need this force, we need this centripetal force pointing towards the center. Now the answer to that is this. The centripetal force, it is true that we need a centripetal force. Now, but it is also true that this centripetal force does not appear from nowhere. Alright, simply because we need a force doesn't mean that there is a force. It's like if I need some money, it doesn't mean that I'll have some money. I have to find some way to get it. So in this case, I know that when I set this up, I can even see it in going around in a circle. It doesn't mean that just because I want it to go around in a circle, the centripetal force would be there. It would just appear because I want it to. The way to look at this problem is this. Okay. As we have seen, there is this force pulling it down, this weight, and there's this tension. So we know that there are these two forces. We can see that from the setup. Now there is not a third force acting on the stone that pulls it towards the center. There is not. Now, but the reason why it can go around in a circle, therefore, alright, the logic that we need to use here is this. The reason why the ball can go around in a circle must be because of the existing forces, the known forces, the force that we know, that we are sure are acting on the stone, that we can see are acting on the stone. okay, maybe we can't see them, but we know that there is the weight and there is a tension. So these are the only forces that we know that are clearly there. There isn't any other thing actually acting on it. We're assuming that no one is going to put a finger on the ball and push at it. So we are sure that these are the only two forces. Now, if these are the only two forces, then the obvious question is, I thought we need a centripetal force. So where is that? Now, the answer to that is actually very simple. The centripetal force must come from the existing forces, meaning these two. Okay, so whatever force we have, whatever force we know, in this case the weight and the tension, those must be the forces that will provide that centripetal force. And that's how it works. Like the previous in the previous session when I talked about swinging a stone attached to a string or over my head, that centripetal force, if you remember, came from me, my hand pulling on the string. But it doesn't just come from nowhere. It comes from that string and comes from my hand. So in this case, we have this string, we have the weight. So it must be these existing forces that provide the centripetal force. Okay, so but how do these two forces provide the centripetal force pulling the ball towards the center? The answer is simply the resultant of whatever forces, of all the forces actually, that we know are acting on the ball. Now let's have a look at the resultant of those two. In order to find the resultant of these two forces, now I need to think about maybe using a parallelogram law or the triangle law. So in this case, the two vectors are already attached, are drawn with the tail to tail, but I'm going to still move them away and draw it out separately anyway to avoid making this confusing. So I'm going to draw my T there. So that's my tension along the string, and I'm going to move my arrow, my vector for the weights here. Remember that when we move the arrow, we must always keep it in the same direction. Okay, so that's vertical. Of course, when I move the arrow for the T, I must keep it in the same direction, meaning that the angle of this to the vertical must be 30 degrees. I need to be very careful here. Make sure that that's 30 degrees. Okay, if I have a vertical line there, that must be 30 degrees. So here, now, how would I find the resultant of those two forces? Okay, if I try and do it by drawing a parallelogram, I would complete this side by drawing a line parallel to this. I would complete this side and this side by drawing a line parallel to that. Now once I've done this, then the resultant of these two forces must be a force that joins this corner to that corner of the parallelogram. So this must be my force. Not very straight. So I must have force there in this direction. Okay, and this is the resultant. Okay, and the reasoning is this: the existing forces must provide the centripetal force, and the logic is therefore that this resultant force, which I obtained from the parallelogram, must be the centripetal force. Okay. So from here, from this reasoning, we would then continue to see whether it can lead us to the answer. Right? The question being that the question was to find the velocity v. So let's now look at this resultant and think about what it means if it is the centripetal force. So we say, right, this resultant has to be the centripetal force. So if this is centripetal force, it must point towards the center. Okay, so now we have a force. Now we understand, okay, that there is a centripetal force, but it's not an additional third force to the tension and the weight. It is this additional. It is the resultant of those two forces, and it must point towards the center. And if it points towards the center of the circle, it means that it must be horizontal. And if it's horizontal, then this must be a right angle. That's a right angle. That's a right angle. Okay. So we now know this. Now we still need to relate. Still need some connection to this velocity. Now the velocity would be, let's say this centripetal force is F. Now the connection would be F would be the formula for centripetal force. F equals to mass times V squared over R. That would be the relation. Okay. So if we know the radius of the circle, the mass of the circle, and the force, we should be able to find the V. So, right, which reminds me, there is an additional bit of information that we need, which is the radius. So let me give this radius a value. Suppose that this radius, is say this is 0.5 meter. Suppose that's my radius, so quite a long string. Okay, so we have a radius. So let's start. Now we know what we need to find now. With the mass, we have the R. To find the V, we need the force, right? Okay. So I shall try and find this. See if I can find this force from this picture. So from this picture, let's see what we have. We have this parallelogram. We have the angle. Now, let's see what else do we have. We don't know T actually, so that's too bad. But do we know the weight? We know the mass. We know G. So actually, yes, we can calculate this. We know this. We know this angle. We know that this is 30 degrees as well. We know that that's a right angle. So we have a right angle triangle. We know this side of the triangle. In fact, let me just calculate it just to make that clearer. So if G is this, then mg is, because m is that one, 0.01 times 9.81. So that means that this would be 0.0981 of a Newton. So that's my force here, 0.0981 of a Newton. Okay, that's 30 degrees. So with this right angle triangle, actually, I already have enough information, because I know this side and I know this angle, to find F. Because the relation between F and this side is a tangent. So therefore, I know that that F divided by this value, this mg here, is equal to the tangent of this angle. Tangent of 30 degrees. Okay, so this means that I can multiply both sides by mg. If I multiply both sides by mg, this is what I get. and I can actually now calculate f. Okay, mg is that value, 0.0981 times, I can use a calculator to calculate tangent 30 degrees, or let's see, I can use an expression for the special angle. That will be 1 over square root of 3. Right, either way we can find the answer. There will be so many newtons. So now that I've found the force, I can then substitute it into that formula, and since we know the mass and the radius, we can then solve for v squared. So let me complete this calculation as far as I can. So from there, I'm going to continue my calculation in this corner there. I want to find v squared. So I'm going to move r and m over to the other side. So r goes up, m comes down. So I'll get v squared is equal to r goes up, m comes down. Okay, so this gives from values that we already have, we have r from that's 0.5, 0.5 times the f that we have there. So it's a bit complicated. I'll put on the m first. M is 0.01. Right, and then my f is this one, 0.0981 divided by root 3. Okay, and then with our calculator, we can find an answer. But remember that this is v squared. This is v squared. So to find our final answer, we need to take the square root of that. Okay, and I shan't go through the calculation, but you can find the answer, and mustn't forget that the units are meters per second.